Hey everyone, Mr. Armitage here. And so in this video, we'll talk about the confidence interval. In the last video, we talked about the sampling distribution, and we could see how that might start arising to the normal model. But now we're going to delve further into the actual confidence interval. So a confidence interval is an interval. Okay. It's an estimate of where the population parameter may be with a specified level of confidence. So often we talk about the 95% confidence level, and a confidence interval based on 95% would say that we are 95% confident that the population proportion, in this case, is in this range, is between these two numbers. So the example from the previous video was 0.62 for p hat. And since we're going to create a normal model, we need the standard deviation for that, which was 0.0686. But what does all this mean? All this means is that we can take these two values here and treat them exactly as the mean and standard deviation for a normal model. Okay, so that would give us mean of 0.62 and a standard deviation of 0.0686. Now, through the magic of pausing the video, let's see what a normal distribution would look like with these values. Okay, so here is a normal model based on those two values, on those two parameters. Okay, in the middle, we have our mean of 0.62. And then at one standard deviation away from the mean, okay, above the mean, we have 0.6886, and below the mean, we have 0.5514. And then two standard deviations away from the mean, we have above the mean 0.7572, and below the mean 0.4828. And we could keep going, right? Three standard deviations above the mean would be 0.8258, and three standard deviations below the mean would be 0.4142. You could do four standard deviations, and then 5 and 6. You could theoretically go on forever because it's the normal model, even if it doesn't make sense in terms of proportion. But in this situation here, okay, remember what the percentages are for the normal model. Within one standard deviation, so from here to here, we would expect about 68% of our data to be between those two numbers. Between two standard deviations, we would expect about 95% of our data. And between three standard deviations, see if I can actually draw this, we would expect approximately 99.7% of our data to be between those two numbers. Right, we would expect all of our samples to kind of fall in there if this was the true value of the population proportion. we already have our confidence interval here. All the confidence interval is saying, okay, to what level of confidence, or to a certain level of confidence, we know that the population proportion should be between these two numbers here. So we can already see what the 95% confidence interval is. The 95% confidence interval is the two numbers that are 2 standard deviations away from the mean, or 2 standard errors away from the mean, kind of. So our 95% confidence interval be between 0.4828 and 0.7572. So we are 95% confident that the population proportion of the fish from our previous example will be between these two numbers. Will be greater than 0.4828 and less than 0.7572. That's all this confidence interval is. Now we can generalize it, okay, and make it a little bit more, well, however we want to calculate it. And so our standard error was the same thing as the standard deviation. So the square root of p hat times q hat divided by n. And then our margin of error is simply how far away from that center value do we want to be. So the margin of error is the z-score associated with that percentage, okay, some sort of critical z-value times the standard error. And so in our example up here, we used 2, okay, for our 95% confidence interval, because 2 standard deviations away from the mean would give us about 95% confidence. And so finally, our confidence interval for a specified confidence level, the middle, plus or minus the margin of error. And so the lower value is the middle minus the margin of error, minus 2 times that standard error. And then the upper value will be 2 times, or plus 2 times that standard error. But honestly, even though we said it was 2 for 95%, it's not really, right? So let's look at what it actually would be. Okay. 2 is a nice, easy number to use, so we use it a lot for this. Okay, it's simple, but it's not really the correct one. So if we want the correct value for our z-critical, and this is also how we can find any different confidence interval, right? We're going to want to see, okay, what are we doing in the first place? Well, let's just start with 95% so we can see that. Okay. So in our 95% confidence interval, or for 95% confidence, okay, that represents this red portion here in the middle. Okay. We are 95% confident that it will be somewhere in here. Well, we need to figure out what these values are. Okay? So on the right side, that would be the positive one, right? And on the left side, that would be the negative one. So what are those values? Well, remember that our table for z-scores only has values to the left? And by to the left, I mean, the area to the left, like this, or like this. Okay, well, how do we use this to get those values there? You may already know, or you may not. So let's figure it out. Right? So what's left over from this 95% is 5%. Right? Straightforward. Okay. So 5% is contained in both tails. Okay. It's contained within two separate tails. Okay. And when you add up both tails, you get 5%, which would mean that each tail individually would be 2.5%. Okay. So now let's find our value. Okay. So we know that, well, there's two ways we can do this. Okay. So the first way is we know this 2.5% is the same as 0.025. Okay. So let's go find that in our negative table entry. Okay, so, oh, nope, that's too small. Okay, we want 0.025. Okay, so here I'm in the negative 2s, negative 1.9s. I know it's going to be about there because I know it to expect it about negative 2. So let's try to find the closest one to 0.025. As we look, oh look, we found one exactly, 0.0250. Awesome. So that's on negative 1.96. So then we know that this z-score is negative 1.96. And so on the other side is going to be positive 1.96. Okay. That only works because this is symmetric. Okay. If this was not symmetrical, okay, if we had more on one side than the other, or we were doing what is called a one-tailed test, we'll see about that later. So like all the 5% was contained in one side, well, then we need to figure out what this upper value may be, if that's the one we're looking for. Okay, so let's see here. What's the area to the left of that value, of that z-score? Well, that's 95% plus 2.5%, or 0.975. So now we do the same thing with our z-score table. Only now we're going to look in the positives. Okay, so let's find let's find in the middle part here 0.975. We know about where to expect it, right? 0.9750 right there. That's in the positive 1.9 row. And that sixth column, or that sixth column there. So positive 1.96, which is what we calculated right there already. So that would be the positive version. And then we'd know, okay, negative, same thing. So the actual 95% confidence interval isn't multiplying by 2. It's the 95% confidence interval for a proportion. It's not really p hat plus or minus 2 times the standard error. Okay. It's really plus or minus 1.96 times the standard error. That's why we were multiplying by 2 before. It's a simple number. It follows the 68, 95, 99.7% rule. But really, when we get down to it, the actual critical z value we need is 1.96 for a 95% confidence interval. So this means we can find other values as well. So let's, for funsies, let's do the 98% confidence interval. Okay. Now, you probably wouldn't do this. Let's not do 98. Let's do the next most common version. Okay, 99% confidence interval. So now we want to be 99% confident where our population proportion would be. Okay, well, we know that, okay, we're going to have p hat plus or minus some value times the standard error. Okay, so what is that value? Well, let's draw a quick picture. Okay. Here's our picture. Okay, if we're doing 99%, okay, so that means in the middle here is 99%. So outside of that is 1% in both tails. So that means each tail is 0.5% or 0.005. And so now on our z-score table, okay, we're either going to look for 0.005 and just use the negative version, or we'll look for the, here, 0.995 and get the positive z-score, right? 0.5% plus 99% is 99.5%, so 0.995. I'll go ahead and use the positive one because we're already here. Okay, so 0.995. Okay, it's probably going to be here. Okay, so it's between these two. Right, here we have 9949, and here we have 9951. So we could go between them, or we could just pick one. It's not going to change too much right now. Okay. But either way, okay, that's in the 2.5. Okay. And that is between the 7 and the 8. So that'd be let's say, not 0, 2.57. Okay. Or actually, we'll make our confidence interval a little bit wider, 2.58. And so now if we calculated this confidence interval, you should get, using the same values as before, of p hat being 0.62 and our standard error being 0.0686, should somewhere around here. So our 99% confidence interval for this same sample would be that we are 99% confident now that the true population proportion is between 0.443 and 0.797. So we would need to figure, well, we can't figure out the true population proportion usually, but we know that we could theoretically by just counting all of those values before. But in this particular case, being 99% confident now, the true population proportion is either in there or it's not. Okay? But there's no way to know, technically. So we're just stuck with that, and that's all we have. Now later on, we can use this to make certain claims about whether a particular value for the population is supported by our sample or not. But right now, we just have this confidence interval.